Hello guys. Quick update. What's going on? I am planning to build a push-pull Tesla coil. I have two designs basically here. This one is using two chokes, and I'm not sure if it works. With the feedback tabs, I'm trying to emulate the around 1:3 ratio. I'm trying to emulate the 1/3 ratio of the feedback of a traditional Tesla coil, and because I have quite large capacitors, I think. I'm not completely sure. I could even I have acquired five doorknob capacitors. Hold on, let me get them. I got five of these doorknob capacitors here, and yeah, of course, Soviet ones. These are pretty good quality. I'm now homeless because I can no longer afford to pay rent, of course. I mean, yeah, these were expensive. I paid around 68 euros for five of them, but they're good quality capacitors, and I know that that purchase didn't go to waste since they're good. Of course, they're good capacitors, so they won't break. Um, so I plan to use them in the feedback section because that is the most problematic part of this design, because if the feedback arc's over, of course the full B plus goes to the tube, but I'm trying to fix that using two systems. Of course, instead of having a resistor here for the feedback, well, a pull down resistor basically is what this is acting, from my understanding. Instead of having a pull down resistor, I'm gonna use an inductor because it has a low DC resistance, which is perfect to start up the tube, and it would present a high enough impedance to the high frequency. So I am aiming, because this is a low frequency Tesla coil. It's only 160 kilohertz. I need to have of course, larger chokes to account for that. Um, so that is a big issue. I should have had a higher frequency. But with higher frequency, because this Tesla coil is going to be quite big, I think with the high frequency I could introduce a lot of more problems because of parasitic inductances and capacitances. Uh, I'm unsure about this. I'm unsure about the chokes for the feedback resistors. I might change that to incandescent bulbs. But the thing is, if the bulb goes out, the only thing really pulling it down enough for the grid is the grid impedance, and I don't really like that. And if there's an arc over across the capacitor, yeah, the bulb is dead, and I don't want that. I'm unsure of this design. I know that the basic design works. So this is a push-pull Hartley oscillator. But the only designs for a push-pull Hartley oscillator I've seen is basically this design with with a choke that goes to the center tab, and I'm unsure which one is better. I'm going to go for the two choke one, since it offers, well, it's less annoying to have more tabs on the coil, like this one. This one has 5 tabs, as you can see, and this one only has 4, and I would rather prefer such a system because it gives more flexibility. So if I maybe want to add another turn, I don't need to recalculate the amount of turns. I just add the turn and maybe move only 2 tabs instead of 3. Well, 4 in total, but you know what I mean. Yeah, so I'm gonna use 2 GU-81 tubes, not the GU-81M, the one before that. And if you look on the data sheet, it shows 2 capacitors inside, and you can actually see them. There's an X-ray picture of a person who put the GU-81 and the GU-81M. We basically X-rayed them, and you could see 2 capacitors inside of it. Hold on, let me grab the data sheet. So this is the data sheet for the GU-81M. So nothing. This is the classic data sheet you find online course, and this is an original Soviet datasheet. And when I bought 2 tubes, and it included the datasheet. So this is, you can see the 2 capacitors here. This is a datasheet from 1966. And this is the later one from 1969, and it's a GU-81, not GU-81M, so it has 2 capacitors inside to decouple grid 2. According to my friend Modness, also known as David Pavian, this is not a problem for any HF application. I worry that I may break the capacitors with the negative poles, but so many people have messed around with the GU-81 tube, and so far I've never encountered any online thread or heard from some people that these capacitors like to short or get damaged in any way. So yeah, I'm gonna be trying out the schematic. I'm gonna try to get building tomorrow or in the near future. I will probably not finish this in this week because it's a big project, because I need to wind a few chokes. You know, these ones and get their value right. I have 2 pieces of ferrite. I had a ferrite rod antenna from a radio. Well, I bought a lot full of capacitors, and there was also an antenna in there, like a rod antenna. Thing is, I was stupid, and I accidentally dropped it a month later, and you see it broke. I've removed the extra stuff on the coil, the coils, some other chokes. You can see how very nicely this one is wound. I may reuse this in some project. And I have 2 pieces of ferrite. So, and I also have these steel rods. These are ferromagnetic, steel. And yeah, you can see by the weight that this one is way lighter than this one. So if I wind a coil on this, it will be the same inductance. Maybe we'll have more inductance per turn, basically. So I am hoping, I'm hoping that I can use these for the chokes. I need to wind less wire on it instead of this ferrite. Though I'm not sure what to use this ferrite for now. I may use it for something else, or maybe I'm not going to use these pieces of steel. I'm unsure about basically everything in this design. I'm unique. So people most often use 2 microwave oven transformers for the GU-81 tube family, basically, to achieve a longer arc length. But what I'm doing is the strange thing of trying a new topology. Yeah, I also have already designs for how to modulate these, also suppressor grid modulation. Like I did with my current Tesla coil, I even have it set up for suppressor grid modulation right now. So yeah, I will use a transformer with a center tap, of course, and 1 grid high, 1 grid low. So yeah, it will get modulated with a basically push-pull system as well. Yeah, I think I'm going to go for this schematic. I am also worried about the negative peaks coming from this capacitor here on the grid, because the grids can limit a positive voltage, of course, because it's basically similar to a diode junction and a resistor in series, but they cannot limit negative voltage. So I will have a protective spark gap that will be tuned to around 2 kV to protect the grid if, let's say, there was too much negative voltage, because I basically do not know how much the voltage on this coil rises under resonance. And this is why I'm also picking doorknob capacitors here, because I think 15 kV should have enough tolerance even if I go above 15 kV. My friend Modness or David Pavian had direct flashovers from the secondary onto the capacitors, and they survived. So I'm hoping that they will also survive if something was to go horribly wrong. As I've said, this will have a low DC resistance, but a higher AC impedance. So I'm hoping that if there is a arc over something, it will just show to ground. And the good thing about these tubes is that at no grid bias, so the grid directly pulled to ground, and with the anode at like 1 kilovolt or 3 kilovolt, they're only a few milliamps. So around the 3 kilovolts, maybe like 20 milliamps will flow through the tube. 20, 30, or maybe 50, that's like nothing. So the tubes, so these tubes cannot destroy themselves in a semi-pentode or triode configuration. I mean, the semi-pentode configuration with the suppressor grid to ground. I'm gonna be running them in a triode mode because I do not have a second microwave oven transformer. Well, I do, but it's not the same size, and you want them to be matched. And the smaller microwave oven transformer already got pretty hot, like burning hot, when I ran this. When I switched out the smaller one for the big one, it was running way too hot, and it wasn't performing as nice as the big one. So yeah, I'm gonna be using the same power supply basically, but with another filter capacitor, well, doubler capacitor, but you know. I will also, of course, have a voltage meter on it and a current meter. So I'm unsure exactly about the microwave diodes, how much current they can handle. It depends from diode to diode, but I haven't really researched, but the one I have in there now didn't explode at 500 milliamps, so I'm hoping it will fine. I have another one that is 500 milliamps, and I could potentially put two in parallel with a balancing resistor of, let's say, 50 ohms. I have a box full of power resistors, wire wound power resistors, so 50 ohms. That should be fine at like no current. That would be like maybe like around nothing. 50 ohms at like 500 milliamps. That's gonna drop just a few volts, I think. So I'm going to be using the I'm going to be using my patented IRF bypass capacitor. The thing I usually refer to like as a pipe bomb, even though it's not a pipe, but you know, it's basically a bomb. So yeah, we'll also have the light bulb on there to tell me if it's on. You can see some parts of the setup changed. Yeah, I'm gonna be using the same resonant capacitor. So it's this one right here. This is not a Soviet doorknob. It's technically a doorknob, but you can see that this one is a 2.5 nanofarads capacitor, and doorknob capacitors of 470 picofarad are basically the same size. And I know doorknob capacitor is just two circular plates insulated, and this one has a higher voltage rating and higher capacitance, which means that this has to be multi-layer of some kind, and it gets hot during operation. So it has higher loss or ESL or ESR to obviously cause a loss. Yeah. I'm gonna be using the same one. It is fine. It gives me good performance, good enough performance. If the performance around the same, I might also buy more doorknob capacitors to put together a bank of it. Yeah, that's pretty much everything I wanted to say. So thanks for listening.